Hi, Rashid here. Um, welcome to the channel. So, the next few videos in the STA series, STA training series, are going to be about timing issues. So, I thought, why not I come and give you some theoretical background of that. So, there won't be any drawing. I won't be sharing my monitor, and we're not gonna do anything practical. I'll just talk about it for the next 10 minutes or so. All right, so there are type of ECUs. So functional ECUs and timing ECUs. So let's talk about functional ECU first. My topic is timing ECU, but you need to know what is functional ECU. So let's say your design is big, okay? It takes starting from a synthesis all the way to finishing it with fill and getting it ready for tape out and maybe integrating into full chip, or it's doing a tape out standalone. That's the entire process going to take another 2 weeks. Okay, and on this design, on a previous iteration, previous synthesis and placement route iteration, you spend a lot of time doing custom fixing, hand fixing for timing, for DRCs, moving cell, this and that. And we are just 1 or 2 days away from tape out. And what happens is the RTL validation team, emulation team, or somebody finds a bug in the RTL code. Then your leadership team decides that, okay, that bug needs to be implemented in this tape out, in this design. So what you do, what are your options? Okay, one option is, a simple option is, okay, RTL guys, update RTL, and you take that again from synthesis through placement, routing, CTS, and then sign off timing, and do everything that you did before, and then get that ready for tape out. Another 2 weeks is a long time, first of all. You did a lot of custom changes, hand fixes, and all that. So you don't know if something else gonna come in this design. You start having some crashes or some new timing violations start appearing, or your design congestion was pretty bad. And what if you retake it and the new problems, right? So you want to avoid that. What the other option you can take is, if the change is small, few gates, depends on the change. Maybe sometimes you can take few hundred cells as well. So what you do is surgical operation. Somebody needs to generate the change in the net list. Okay, you get that change and you try to open your router database and you make a change on top of that. Okay, so you are adding a logic, you're probably removing some logic. Now this new logic comes in. Rest of the logic is optimized previously for the previous logic that you had there, but you're updating that logic. So things can work, and as I said, it depends on the change. How big was the change, or how complex was the change? Or you might get some new path. Now you need to fix those paths. Tool didn't optimize them before. This is your surgical way of adding those, right? So you may get it sometimes generating that net list. Sometimes that surgical operation might take even longer than if you do go back and resynthesize your design, right? But it really depends on your circumstances. That's why I say that physical design is about automation. Once on a new design, you have done experiments and you have decided what tool options, variables, path groups, or all the stuff that you did to converge on a design, you better script that. Because if new RTL comes, you don't need to do any hand fixing. Maybe very small, but most of the design will just go. You press the button, okay, and it goes through it. Every report is generated, log generated, and you pretty much, your recipe is in a best condition, and RTL comes in, synthesis, placement, CTS, routing, everything's done. So a good physical design engineer needs to have a good physical design recipe, a good automation in place. Okay, everything in a proper area are documented, what changes you did, you didn't, and everything is in decal or in a script. Okay, that's a good as a physical designer, but sometimes it's not always possible, right? It depends on the circumstances under which you did your place and router synthesis or timing or DLC fixes, right? Okay, so that was a functional ECO. So of course you need to first somebody need to generate a change that is generated through the formal equivalence tools. After you make a change, you need to verify it again just to make sure your updated netlist has the same functionality as the updated RTL. And when you do a diff to the previous one, it is the same change that you did. You didn't change something else. You didn't make any other wrong connection. So you need to be super careful on that. Okay, so that is functional issue. The others are the timing issues, which I call timing issue, which is what I'm going to talk. We'll look into the flow and we'll look into an example in the next few days. The timing issue is you still have your routed or finished database, a filled database, okay? But now you bring it into Tempus, into Primetime, into the sign-off STA tool, okay? You figure out that you have some new max cap violation, max trans violation, new small remaining setup violations, some hold violations. Okay, remember the last week when we look into some of the max cap violation on the test case that I'm looking into, figure out that inside the implementation tool, tool was not seeing those violations, but in the sign-off tool, we saw a lot of max cap and max trans violations. So you can have a surprise like that. Now, ideally, you need to go back and make sure your implementation tool reports exactly the same thing as your sign-off tool. But if you have time, you can go back and replace and route and everything. But sometimes you don't have time to go back and start doing those things again. And you really want to do optimize things now within the STA tools. STA tools have the capability to insert buffers, inverters. They can size cells, they can swap cells with some other type of cells, and as long as functionality is the same. Okay, so those things STA timing issues can be done. They can do that. They can fix max cap trans, they can fix some setup, they can fix hold, they can also fix the leakage power by swapping cells which are low leakage cell, for example. But as I said, sometime ideally your placement, your implementation tool and your sign-off tool should correlate well. But not always that is possible, because sign-off is sign-off, okay? It is much more accurate. It will have sign-off extracted design, RNCs will be sign-off. The timing engine is sign-off. Okay, so a lot of things are sign-off. There is, even when you do all your best to have a good correlation between implementation and sign-off tool, there's always a possibility that you have some surprises. Okay, so the story and the moral of the story is that you will have to fix some things eventually in the sign-off tool. And this timing issue is the process of fixing that. So concept is simple. As I said, Tempus, Primetime, or these sign-off STA tools have the capability that they can look into timing path. They have analyzed it already, right? They have information about the standard cells. They have information about the max cap, max trans, what other cells are available, what other possibilities are. So they can fix DRV, okay, which is max cap, max trans. They can fix setup. They can upsize cells on a timing path, okay, and then they can improve, right? They won't be able to do a lot of optimization, but they can do last remaining violation that implementation tool for some reason didn't do. Then they can fix hold. They can insert buffer at endpoint or start point. Then leakage optimization they can do. For example, if your leakage power is high, they can replace those paths where your setup margin is high and they're passing pretty comfortably, right? So instead of leaving 1 nanosecond, 500 or 300 picosecond plus margin, what you can do is you can consume some of the margin and replace some of those cells with the low leakage cell. Low leakage cells will have higher delay. But it's okay on your non-critical part where you have plenty of setup slack, you can fill those ones. So the flow is that inside the sign off tool, you generate, there are commands that you can do DRV fixing, you can do setup, you can do hold, you can leakage. So once you run those, tool is going to spend some time and going to create ECO files. Okay, it's going to update the database, and it's going to create a tickle file that will have all those kind of cells, inserts, buffers, insert, inverters, swap cells, or size cell type of command. Simple kind of optimization, right? That tickle file that it generates, you need to take that back into implementation tool, and there your sources, and you do an incremental or ECO route on it. So first, if for example, if this new cell it added is a bigger than its previous location, now you need to find the legal location for that. So you need to do legal placement, and those nets which change, okay, you need to route only those one. You're not going to do any optimization, anything, and you're not going to touch rest of your design. Only surgical legal placement and incremental routes you're going to do on those nets. So once that is done in the implementation tool, then you're going to de-extract that for that and bring it into the sign-off tool and verify that. Now sometimes you probably need to fix a little bit more, so then you go into second iteration. So within 2-3 iterations, your whole design should be pretty much done. And maybe after that, there are some small hand fix required type of violation that you have to open and fix, because tool is not able to open close everything. But that's your flow. Now, even the timing issues are two types. One are the logical issues. The others are physical aware issues. Okay, logical is the one where when you are in the sign-off tool, for example, Tempus, right? Your design doesn't know the physical location, relative location of different standard cells, macros, and everything. Okay, that information is not there in the Tempus tool. So what the sign-off tool is going to do, sometimes I call Tempus, sometimes sign-off is the same thing. Okay, so sign-off ST tool, what it's going to do, it's going to do some logical changes, size cell, swap cell, insert cell, and update those. And you go back in your design, let's say there's a plenty of space. I mean, that cell moves here or here, and there are closer location, doesn't make a huge difference, right? Now, if your design is very congested, high density, and there are very few spaces, and there's a possibility that that space that it moves is far away, then there's a big difference in the delay with what the sign-off ST tool assumed and you actually see on your design, right? Because it made a big movement. Now it's important that Tempus or sign-off tool sees that, so that it knows that, okay, I'm going to move it to far away, so that is how much delay it's going to have. So in that case, you want to do physical aware ECO, because you want to make sure the Tempus or sign-off session actually knows the location of each cell, and it does give me a better ECO so that I can close my design quickly. So that is physical aware ECO, and in that case, your sign-off or Tempus run needs a dev files, the lab file, the physical information of your design as well as physical information of standard cells. Okay, so with that with that theoretical knowledge, I hope you have understood the concepts. And in the next few videos, I'm going to go into first DRV, then into setup and hold, and we're going to look into logs and report and see how the flow is. All right, thank you so much. See you next time. Bye.